So good morning. Today we will discuss critical radius of insulation. So this is one of the important topic in heat transfer. Generally, insulation applications will be there in industries. One is in minimization of heat transfer. One is excess heat will be accumulated. No? We need to dissipate that heat. For that, we need to have maximum heat transfer rates. So for minimization of heat transfer rate and maximization of heat transfer rate, so we are providing insulation. So first we will see what is critical radius of insulation. So the critical radius of insulation is defined as it is the outer radius of insulation. It is the outer radius of insulation at which maximum heat transfer will be occurring is called as critical radius of insulation. So it is the outer radius of insulation. It is the outer radius of insulation at which maximum heat transfer. So maximum heat transfer will occur is called as critical radius of insulation. Generally, if you provide insulation, heat transfer rate will be minimized. But situations are there. Initially, heat transfer rate will be increasing and reaches maximum value, and then it will be decreasing. So that condition where we are getting maximum heat transfer is called as the radius is called as critical radius of insulation. So here, for minimization of heat transfer, if you want to reduce the heat transfer rate, generally in case of thermal power plants, steam will be carried. In case of refrigerant, refrigeration air conditioning systems or AC systems, so refrigerant will be carried. So if you want to minimize the heat loss, efficiency will be goes on increasing for these systems. So if you want to minimize the heat loss, insulation is provided at a radius greater than that of the critical radius of insulation, so that we are minimizing the heat transfer rate. So for increasing the heat transfer rates, insulation is provided at a radius equal to critical radius of insulation. Generally, in electrical transmission lines, due to flow of current, heat will be accumulated in the wires. So if you provide insulation at a radius equal to critical radius of insulation, so maximum amount of heat will be dissipated to the atmosphere, so that the given systems will be in the safe condition. If you don't provide, heat will be accumulated, so the damage of the wire or melting of the wire will be takes place based on the amount of heat accumulated. So in order to derive the expression for critical radius of insulation, so let us consider an insulating layer as shown in figure. So this is the insulating layer. This will be the insulating layer. So here the various parameters of insulating layer are mentioned here. So this will be the insulating layer. This will be the insulating. This is the insulating layer. This is the insulating layer. So this will be the insulating layer. So here R1 and R2 will be the inside and outside radius. T1 and T infinity is the inside temperature and outside temperature. K is the thermal conductivity of the insulating material. So here the insulating material is exposed to atmosphere. So T infinity is the atmospheric surrounding air temperature. Next one is H is the convective heat transfer coefficient. So the equivalent thermal circuit for these conditions will be the one is the resistance offered by the insulating layer, that is called as R insulation. So Ti is the inside surface temperature. Since it is exposed to air or surroundings, so T infinity and convective heat transfer coefficient, convective resistance is there, or convection. So this will be the equivalent thermal circuit for these conditions. So when heat is flowing, heat is losing or heat is flowing, the heat loss formula will be Q is equal to temperature difference between the terminals divided by resistance across this one. Since resistance are in series, now you need to add all the resistance. We know that R insulation is in case of cylindrical coordinate systems, ln of R2 by R1, 2 pi KL, plus convective resistance is given by 1 by HA. Here HA is 2 pi R2L, 2 pi R2L. A is outside surface area, that is 2 pi R2L for the cylinder. Now you take 2 pi L common. So if you take 2 pi KL common means this is 2 pi KL. This 2 pi KL common means the equation will be simplified to T1 minus T infinity 2 pi KL, 2 pi KL ln of R2 by R1 K by HR naught. So for maximum heat transfer rate, the denominator should be minimum. That is the condition that the denominator should be minimum. So when the denominator should be minimum means its first derivative is equal to 0. So now you differentiate the a denominator with respect to R naught or R2, both are same only. Now you differentiate this one with respect to R2 means, so you will find d by dr naught of ln of R naught by Ry, R naught by R1 or R2 by R1 plus k by hr naught is equal to 0. So R naught means outer surface area, outer radius. So here you will get log a minus log b, no, ln of R naught by Ri. So log a minus b, ln of R naught minus R1 on this one. So since we are differentiating with respect to outer radius R naught, this value will become 0. Differentiation of R naught will be 1 by R naught. Differentiation of k by hr naught will be k by hr naught square. So here 1 R naught and 1 R naught will be get cancelled. Therefore the R naught is 1 by R naught is equal to this thing you will get. From this we can find R naught is equal to k by h. That is called as critical thickness of insulation or critical radius of insulation. RC is equal to k by h will be the formula for critical thickness of insulation. This is a formula for in case of cylindrical coordinate systems. So if you see now, I told you now, when you keep on providing insulation, so we will have R resistance offered by the insulation is given by the formula. R insulation is equal to, the formula is this one, ln of R2 by R1, ln of R2 by R1 divided by 2 pi KL. This is the resistance formula. Next one is R in R naught formula, or convection formula will be ln of 1 by HA, 1 by 2 pi R2L, 2 pi R2L. So if you keep on providing insulation means this R2 value increases. When you keep on increasing the insulation means the outer radius will be goes on increasing. This is increasing. So when you increase this value, R insulation will be increasing because it is in the numerator. When you keep on providing insulation, R insulation will be increasing, and this R convection will be decreasing. When R convection will be decreasing, so R insulation will be increasing faster than R convection decreasing in the initial conditions. So here since it is decreasing, this will be increasing. So when heat transfer is increasing means the resistance will be decreasing. So initially R convection decreases faster than R insulation, resulting in decreasing in the total resistance. Total resistance formula will be R is equal to R insulation plus R convection. So initially the convection will be dominating, and this will be not that much dominating. Therefore initially if you keep on providing insulation means what will happen, R convection will be decreasing faster than R insulation, resulting in decrease in heat transfer rate. So when you resulting in decrease in resistance. When there is a decrease in resistance, the heat transfer rate will be goes on increasing and reaches the maximum value. So when it reaches a sufficient radius then this R insulation will be dominating, and R insulation increases faster than R convection, resulting in increase in resistance, and when resistance for the heat flow is increasing means the heat transfer rate goes on decreasing. Therefore the point where we are getting maximum heat transfer rate is called as the critical radius of insulation. For cylinder it is k by h, just now we have seen. So we need to provide insulation at critical radius of insulation if you want to minimize the heat transfer rate. If you want to maximize the heat transfer rate, just in case of electrical transmission lines. If you want to decrease the heat transfer rate means, so we need to provide the insulation at a radius greater than the critical radius of insulation, so that we will minimize the losses and we can improve the efficiency. For spherical coordinate system the critical radius of insulation is given by Q is equal to temperature difference divided by resistance across Z1. So if you differentiate the denominator now for maximum heat transfer rate, so you will get this is the thing. So since we are differentiating with respect to R1, R2, this value will become 0. So you will get this one. And if you send that side now, different 1 by kr2 means 1 by kr square. This one, if you send this side now, differentiation of 1 by r2 square will be minus 2 r2 cube. And finally, if you send this side, so from this you will get the expression for this one now, critical thickness of insulation 2k by h for a spherical coordinate system. Spherical coordinate system. Spherical coordinate system. So like this, we are deriving the concepts of critical thickness of insulation. I hope you understand this one. Thank you. If you have any doubts and clarifications, you can contact me at the WhatsApp number. I am Dr. T. Hariprasad, Professor of EME, 9885404470. This is my email ID. So if you like this video, comment and share and subscribe. Thank you, Anandal, for watching this video. Thank you.